So lesson 1.5, let's just call it 1.5a because, like I said, we're going to finish it on Monday. Lesson 1.5 is called parametric relations and inverses. And I kind of like the title of it because it says parametric relations, and we actually talked about what a relation was yesterday. And we call them a relation because we can't necessarily call them a function, right? You can represent a relation in terms of x squareds and y squareds, and I specifically told you yesterday that your graphing calculator cannot graph things that are not functions, right? I said that in this class period? Did I? Well, the reason why it can't is because in the default mode that it's set up to be in, when we were graphing stuff, we were using the y equals button. But y equals assumes that something is a function. But if you were to change the mode of your graphing calculator, you can actually force it to graph things that are not functions. Because you could put your calculator in parametric mode. And parametrics is a way to take a relation, something that's not necessarily a function, and turn it into a function in terms of x and a function in terms of y. And a function for x and a function for y, and they're both in terms of a third variable. We use t. And a lot of times we use t because t will represent time. So for any of you that are in physics, this might look familiar to you because when you talk about projectile motions in physics, a lot of times you have motion on the x-axis and motion on the y-axis. And t would be the variable there for time. So we have, consider the set of all ordered pairs x comma y that are defined by these two equations. The way this works is, if you would like to know what an x comma y is, you need to plug in a t value. You take a t value, you plug it into the x equation, it gives you an x coordinate. You plug it into the y equation, it gives you the y coordinate that matches that x. And this would give our calculators the ability to graph non-functions. That's how it works. And I don't think I'm going to be showing you how to do that today, but I might show you Monday just because we should have time. Okay? So what we've been told to do here is find the points that are determined by these 1, 2, 3, 4, 5, 6, 7 t values, and we are legitimately just going to plug them in. No fancy mathematics required. And just to make it a little bit more obvious, I'm actually going to call this x of t and y of t because they are functions, a function for x and a function for y. This gives me the ability to say what is x of -3, and that means just plug -3 into x. So we got -3 dropping right there where t goes. Simplifying gives me -2. And then y of -3, that one's a little bit more complex because that one's a parabola for the y values. So we have -3 squared. Make sure that you use your parentheses, otherwise you'll get a wrong number there. Plus 2 times -3. Quick maths. 9 minus 6, so 3. So when t is -3, you get the ordered pair -2, 3. And we're just going to do that 6 more times. Now you're wondering why. Well, because part C says to graph it. This would give us the ability to graph non-functions. Let's see, what are we doing now? Next coordinate. Oh, cool. So we're just doing -3 through +3. All right, so x and y of -2. Dumb quadratic, making life difficult. So is that 4 minus 4? Looks like 0. And I'm not going to be able to fit all this in this space. Unfortunately, I'm going to have to clear to make space, just because you guys can write smaller than I can. This gives me this coordinate, what is it? -1, 0. Now, you could continue to write it out like this if you'd like to, but there's a really good chance that you could probably evaluate these things in your head without showing the work, right? I'm assuming most of us can. And Actually, let's just say I'm assuming everybody can because you're pretty smart cookies. That's why you're in this class. So I tell you what I'm going to do. I'm going to stop showing all this work, and instead I'm going to list this thing as a t-table because that's what I would expect you to do in your homework. I don't expect you to show all this work. I was just showing you how it's done. The t-table, which makes life easier, so we'll just be like ... right? And we'll just make a t-table over here. So the way it works is you have a t with corresponding x's and y's. So -3, -2, -1, 0, 1, 2, 3. And we've already seen what we get when we plug in -3. It gave us -2, 3. We saw what we got when we plugged in -2. It's -1, 0. In the essence of time, and like I said, assuming that we're all pretty smart people and that we can, yes. Oh, you don't have to ask. Yeah, just go. I'm not the warden. So I'm just going to fill out the rest of this t-table because I'm assuming you all can add and multiply. For this next coordinate, we will get 0, -1, and then 1, 0, 2, 3, 3, 8, and 4, 15. If you have any questions about how I'm coming to those numbers, please ask me. Don't be afraid to. Like I said, the plan is to finish these notes on Monday anyway. But I don't think you need to show. I don't think you need me to show all the work. When you're doing your homework, I don't think you need to show all the work either.
I have a question, but it's not about the work you just showed.
Yeah.
If we're finishing this lesson on Monday, is homework number 4 going to be due to today, tomorrow, or Tuesday?
Our homework number 5 will be due on Tuesday.
Number 4.
No, today's number 5, isn't it? Yeah, because this is less than 1.5.
All right. So homework number 4 is due today.
Yes. There should be a Dropbox for it, but yeah, but the lesson that we're doing right now, this is for homework number 5. But since we're not going to finish it today, we'll finish it Monday. Homework will be due Tuesday. As usual, though, I do encourage you to do as much of it as possible before Monday, just because on Monday we're going to run through the practice questions, and it would give you the opportunity to learn from your mistakes. So that's up to you guys, though. I'll leave that up to you. Now, part B, which is probably the most important part of this skill, says to find an algebraic relationship between x and y. And this is usually called eliminating the parameter. So we call the variable t the parameter. And what we're trying to do is figure out, can we write an equation that is only in terms of x and y using algebra skills? Can we eliminate the parameter? And then afterwards, once we have done that, the next part of the question says, well, is y a function of x? So how do we eliminate the parameter? Well, it's an Algebra 1 skill. I am just flat out of space. Can I clear what's up there right now without anybody panicking? No one will freak out? No screams of horror? Okay, good. So we're going to get rid of that. Maybe. There we go. Okay. I need to be able to see my equations. Eliminating the parameter works like this. You go, I need to figure out a way to make the t's disappear. For the way this one's set up, your best option is good old substitution. Because if you knew what t equaled, you could plug it in for one or the other. For example, right up here, wouldn't it be really easy to just subtract 1 from both sides and say that t equals x minus 1? And if you know what t equals, and you see it's just in terms of x, you could substitute in the expression you found for t into y. So for part B, we can say y equals the expression we found for t squared plus 2 times the expression we found for t, and that expression happens to be x minus 1. Hey, my phone's ringing. Yay, I'm popular. There. Alrighty. I want to go ahead and... Did I clean this up in mine? I did. Let's go ahead and clean it up. X minus 1 quantity squared does not mean x squared plus 1 or x squared minus 1. Please don't fall into that trap. X minus 1 quantity squared means x minus 1 times x minus 1. So you do have to FOIL. Again, I'm going to assume that we all know how to FOIL. That's not the color I was hoping for. What it's going to give you is x squared minus 2x plus 1 and then I will distribute this 2 plus 2x minus 2, and you can just clean this up. So y equals x squared. Hey, look at that. The negative 2x and the positive 2x are going to cancel each other out. And then I just have a 1 minus 2, which is minus 1. So is y a function of x? Y equals x squared minus 1. Is that a function? Yes, it is. It's a parabola. So yes. Yep, it's a function. And then we're supposed to graph it. 2 options. You could either plot all the x comma y's that you got from the t-table, or you could just use your knowledge of parabolas and sketch the graph of x squared minus 1. It's the parent quadratic x squared and has been shifted down 1 unit. Oh, that's how I'm going to do it. That is much easier. So part C. Picture not drawn to scale, because who cares? And it looks like this. Ta-da. And if you really cared, x squared minus 1 factors to x plus 1, x minus 1, so we actually know what its 2 zeros are. There. A, B, and C. Ta-da. Yes, ma'am. Yeah. How did we get t equals x minus 1? I went up here to x, and I just subtracted 1 from both sides. Just so I can figure out what t equals and then sub it in. At this level of knowledge for this material, basically substitution is going to be key. I'm trying to remember if there's any other way for you to do it yet, and I do not think there is. Yeah, I don't think there is right now. We use parametrics a lot in trigonometry, graphing trig things that aren't functions. Like you guys, I showed you the parent sine wave, right? Just this. If you use parametrics, you can make the sine wave do this, go up and down. So that's what we use them a lot for, and you could eliminate the parameter using trig tricks. So we'll probably see it again later in the year. All right. Oh, using a graphing calculator. Well, aren't I just wrong? All right, so I'm going to turn on the graphing calculator program. And it is taking its sweet time to open. There we go. So you see that mine opened up in y equals. Yeah, that's not really going to work because you'll notice that R says x equals and y equals, right? And the variable happens to be t. Right now, you don't type this, but right now, if I click the variable button, it only shows me x's. But it would be great if you saw on the variable button that x is not the only variable that button could give you. It could give you a t, a theta, or an n. And the reason why it can do those different things is because you can change its mode. So if you come up here to the mode button and click mode, you're going to be scrolling down to where the word function is highlighted. You see, right now the calculator is in function mode. It can only graph functions. But if you click to the right and hit enter, now the calculator is in parametric mode and it has the ability to graph parametrics. And when you go back to the y equals menu, you will notice now that every one of them has an x and a y. I'm sorry? Okay. So now every one of them has an x and a y option. Click mode, and then scroll down to where it says function, highlight the word parametric, and hit enter. And then I just hit the y equals button, and it took me here. Now, I am not going to graph yet. Don't do it yet, because we could do this by hand. So I'm going to make the point tree again, because it does say it has the exact same directions that the previous example did. Find the points determined by, and it gave us those same 7 t values. So we're just going to make the tree. But you know what I'd like you to notice? I'd like you to notice that they're the exact same parametric equations. They've just switched places. Now it says x equals t squared plus 2t, y equals t plus 1. Well, before they switched places, I had this parabola on the right side. So if they switch places, what do you think we're going to end up with? Let's take a stab at it. Yeah, what do you think? Yeah, a sideways parabola. It's exactly what's going to happen. We literally just switch the x and the y. And if you switch x's and y's, graphs typically turn on their side. So this is going to define a parabola that points sideways, which is clearly not a function. So we already know answer C because we've logicked our way to it. But let's just prove a point. So for part A, I'm just going to go ahead and fill out the, holy cow. All right, hold on. Go home and catch you, you're drunk. Let's try again. There we go. T, X, Y, point tree. I'm just going to fill it out because I know you all know how to do basic maths. -3, -2, -1, 0, 1, 2, 3. And plug in those values in. You get the exact same points you got in the first question, but all the x's and y's have switched place. Yeah.
This like isn't related to this question,
Mhm.
but on the homework,
In the homework.
like the last question, it said like the Kelvin.
Last homework from last night?
Yeah.
Okay, last question.
Like it had us do K times C times X, but there was no C. Like plus X, and then Fahrenheit was like something else.
Oh, C means Celsius.
I know, but like it, but like there was no formula for that. Like it just said.
Yeah, I don't know. I'd have to look at the question. It was probably given somewhere else. The formula is something like 9/5 F plus 32 or something like that, or 5/9 F minus 32. It's one of those two. I'm not. It was probably listed somewhere else. I'd have to look at it, and I'd be happy to look at it here in a little bit. Part B says to. Yeah. Part B says to graph the relation in the plane. And instead of doing this by hand, let's go ahead and use handy dandy graphing calculator. I said graphing calculator. There it is. So we're going to use T. And look, this time when I hit the variable button, it went ahead and gave me a T. It's okay that it's capitalized. Don't worry about that. So T squared, use the square hotkey, plus 2T. I think it's plus 2T. Yeah. Then you just hit the down arrow, and you do T plus 1. Oh, now hold on. Hold on. I'm going to hit zoom 6, because zoom 6 is always a good thing to hit. And wait a second. A lot of my parabola is missing. Not only is it's not even half of the parabola, because the vertex should have been at -1, 0, because before the vertex was at 0, -1. So the question is, where's the rest of this parabola? Huh. Well, here's what happened. Look at what it started at. It started, I can't actually draw on this image, but it started right here. Right there, so that shows up in the video. It started right there at the origin, not the origin, at 0, 1. 0, 1 was the first point it graphed. So let me go back to my stuff here, and I see 0, 1 was right here, and it only graphed the things below that red line. Well, look at what t values that's associated with. No, it graphed the ones that are down here. It started at t equals 0. It didn't.
All positive.
It didn't. Yeah, it only used positive t values. So let's go back to the graphing calculator and hit window. Before, window only did x min and max and y min and max in scale, but now it has added a t min and max as well. So you have to tell it, no, I need more t values. And what t values did we use? We had -3 to +3. So -3 to +3. And t-step is going to determine how smooth the curve is and how quickly this thing graphs, okay? T-step means the calculator is asking you, how often should I be plugging in a t value? And the smaller the t-step is, the smoother the curve will be, but the slower it will take to graph. Generally, I just leave t-step alone, and then I hit graph again. We all know that this thing goes on forever, correct? So in order to see its actual shape, you should probably use more t values than -3 to +3. So maybe -6. I don't know. I'm just taking a stab here. Let's see what happens. There we go. That looks more appropriate.
Why does it say y equals negative y equals 9, 6, 7, 7, 7, 1?
I don't know. That's just the general window that it pulled. I didn't change the t-step. If you change the t-step, the curve will become less curvy or more curvy. Depends on if you make it bigger or smaller. I also want to show you something else that this calculator can do real quick. Let's see, window, and let me slow it down, okay? I'm gonna slow this down. I just got rid of the 1. Now, let's watch what happens when it graphs. I slowed it down. And wasn't that neat, the way it chose to draw it? It started at the negative t's and worked its way around to the positive t's. Pretty cool, huh? I mean, I think it's pretty cool. So let's go ahead and sketch that graph. We already know, because we're geniuses and we already talked about it, but it looks like this. It's a sideways parabola. Whee! Like that, and it goes forever. So is y a function? Is y a function of x? No, this thing fails the vertical line test. Look. Oh my goodness, not a function. So y is not a function of x, but x is a function of y. But you don't have to know that. And it says find an algebraic relationship between x and y, and you would do it the exact same way we did in the last one. You would solve for t wherever it was easiest and substitute in. And well, that would happen this time on this equation. So if you subtract 1 from both sides, you get t equals y minus 1. Basically, the only thing that happened is your x values and your y values switched place. So using a little bit of cheatery, I'll just use the answer from the first example, and I'll just switch my x's and y's. Instead of saying y equals x squared minus 1, I'll say x equals y squared minus 1. There. Because it will be the exact same answer, just having the x's and the y's switched. I have a question for you guys. In algebra, when you switch the x's and the y's, what are you generally doing?
90-degree rotation.
Finding the domain.
A 90-degree rotation, but we don't. You're not wrong. You're not wrong. But we try to stay away from rotations in algebra because they cause non-functions. But why in algebra 1 and 2 did you ever switch the x's and the y's? What was the purpose? What were you trying to find? Because that is the result is a 90-degree rotation. But why were we doing it? I'm sorry, Max? Trying to find the inverse. That is why we did it in algebra 1. All right, so flip the page. Oh, look, inverse crap. How about that? An inverse relation. The ordered pair A comma B is in a relation if and only if the ordered pair B comma A is in the inverse relation. Normal speak, switch x and y to find inverses. Ta-da! And yes, Kai, it does have the net result of turning a graph on its side, basically. That's what it does. Because it's a reflection over the line y equals x. And it's exactly what you're doing. You are switching the domain and range when you do that as well, because every x has become a y, every y has become an x. And I have to tell you a story about how just vicious I am to Algebra 2 kids. So, regular Algebra 2. I've never taught Algebra 2 honors. My very first year teaching Algebra 2 here, I was holding those kids to a standard that was like, you can't see the face I'm making, but it was a high standard. And I tell my students, I will always hold you to an honors standard. I will just teach you at a slower rate. I'm not going to dumb material down because you're not honors. I'll just teach it slower. So, in chapter 5 of Algebra 2, which is where you guys learned about inverses and you had to find them and stuff, you were supposed to have mastered the concept of when you find an inverse, the domain and the range have switched. And this was before I used to test online. I gave them a paper test, and I gave them a question where I showed them, I said like, functions f and g are inverses. Okay, it says functions f and g are inverses. I gave them f of x, and it was some kind of wicked fifth root thing with a fraction inside and exponents inside on the fraction. I mean, it was just nasty. And then I gave them its true inverse, and it was just nasty. And the question said, find f of g of 1. And then I gave them like a quarter of a page, a third of a page of space to do the question. And what's up, Max?
Just one, isn't it?
Yeah, the answer is just 1. Because I told them f and g are inverses, which means they cancel each other. So students that had an understanding of the material realized that it was a trick question. And when I told them that, and this is not meant to be dark, it's a saying, but when I told them that, finally we were going over it, and by the way, I only had one kid get it right, and that was in 4 classes, one kid got it right. One of the kids was like, why'd you give us all that space? And I said, I had to give you enough room to hang yourself, because it's a saying. It's like saying, you give them enough rope to hang themselves. It means give them just enough stuff to get themselves in trouble if they don't know what they're doing. It's a saying. And it was like, yeah, it's a trick question. You don't do any work. And they tried. So all the kids that tried to plug this nasty fifth root thing, which by the way, I'd never taught them how to do, into this other ridiculous polynomial with fifth powers, and just, oh God, it was so bad watching them just crumble and not get it. And the answer was just 1, no work. No, it was a standard credit question. It was funny. It was funny is what it was. Okay, horizontal line test. Wait, horizontal line test? That's right. You heard that correct. The horizontal line test. So just a second ago, we did 2 examples, right? The first one was a standard up and down parabola. It was a function. Why? Because it passed the vertical line test. Now for the next example, we switched x and y, and we got a non-function because it didn't pass the vertical line test. But if you're switching x and y, what that means is every vertical line becomes a horizontal line. Every horizontal line becomes a vertical line. So we could have looked at the original question, which was a standard up and down parabola, and we could have said, we know its inverse is not a function because it fails the horizontal line test. The relations presented in the first 2 examples happen to be inverse relations. Oh, look, a standard up and down parabola and a standard left and right parabola. This was accomplished by switching the parameters, which is what you saw in the first 2 examples. The first relation was a function. Yeah, it passed the vertical line test, but its inverse was not a function. Failed the vertical line test. The easiest way to do that, or the easiest way to tell that without graphing anything about the inverse, is to have drawn a horizontal line through the original, because this horizontal line here would have become a vertical line in the inverse. And since that horizontal line is hitting that graph more than once, the inverse is not a function. Neat, huh? Yeah. And you know what? I feel like that's a good place to stop for today. Oh, you know what? No, we can get through one more example. I just realized there's no math involved. Nah, you got this. So it says, applying the horizontal line test, which of these graphs are graphs of relations that are functions? So you're looking at these 4 pictures and you tell me which ones are functions. Which ones pass the vertical line test? Don't overthink this, guys. Just, what's the first one you see as a function?
2 and 4.
Yeah, the first one, I is a function. And what else is a function?
2.
No, well, 2 is not a function because of this. We hit that thing twice. But the question then asks, which of these relations have inverses that are functions? Now, this means which of these 4 passes the horizontal line test? The oval fails the horizontal line test. Look. I hit it twice.
It's Friday.
Somebody said double I.
Sorry.
He's coming back to us. It is
Yeah,
Friday.
sorry.
We got here 8:30.
Yeah.
Anyway, so double I, which is Roman for 2, double I would pass the horizontal line test. And the other one, somebody already said it behind me, is I. So graph I is a function, and its inverse is a function. It's the only one of the 4 that is a function and its inverse is a function. IV would fail the horizontal line test, meaning if we turned it on its side, it would fail the vertical line test. So yes, while graph 4 is a function, its inverse is not. Awesome sauce. Yeah, I forgot we got out of here later too. I can do so much more math today. Let me see. I think what we're going to do is we're just going to go through this last box of information. We're going to call it early because why not? Yeah, why not? So let's get through this last little box of info. Inverse functions. A function whose inverse is also a function, like graph I. This was the only one that was a function and the inverse was a function. A function whose inverse is also a function has a graph that passes both the vertical and the horizontal line tests. And this kind of function is called a one-to-one function. That means for every x, there's exactly one y, and for every y, there's exactly one x. It uses the definition backwards and forwards. We call that one-to-one because there's one x for every one y, and vice versa. It's called one-to-one in mathematics. If f is a one-to-one function with domain D and range R, then the inverse function, which is denoted as f, what looks like a -1 power, and you would say, please don't say f to the -1. Please don't say that. That's not what that says. That says f inverse. But Mr. M, it looks like an exponent. I know it looks like one, but the dead giveaway that it's not an exponent is that f is not a variable. Okay? Only variables and numbers can be raised to exponents. F is not a variable. F is the name of something. Let me scroll just so the cheap seats can still see. Then f inverse is the function with domain R and range D. And this is what Kai said just a minute ago. He said, doesn't that mean that the domain and range have switched? Yes. See, the domain of f is the range of f inverse. The range of f is the domain of f inverse. The domain and range have switched places. What this means is f inverse of b equals a if and only if f of a equals b. And remember I told you that mean question that I gave those students on that Algebra 2 test? On the same test, I gave them a wicked mean f and its wicked mean inverse and called it g. I said the domain of f is, and then I just gave them some interval, and then I said find the range of g. And again, I gave them a lot of space. For the kids who knew what was happening, they understood that I gave them the answer when I said they are inverses. So I said the domain of f is blank. Find the range of g. And you could just see their ears smoke when they got to that question. And 1 or 2 kids were like, oh. And they just wrote what I gave them, and they left this much space on the paper blank. Because it's funny, you know. I think that's a good place. Now, on Monday, what we're going to do is actually find f inverses. Okay? Okay.